Section 7.5 is Systems of Inequalities. What you have done before, we're doing them in the XY plane, but we're going to be more careful about finding the vertices of the solution regions on each of these. But before we start, I'm just going to remind you that if it has the equal sign, that normally means that when you graph it, it's going to have a solid line, or if it was on a number line, it would indicate a closed circle because it can equal the value on the boundary line or at the critical number. If it doesn't have the equal sign, it's going to be dashed or it's going to be an open circle. What else? Oh, I'll just remind you what the symbols mean. This means less than. Some of you have learned to graph that. You shade the lower side of the boundary line. If it's going this way, it's greater than. And some of you have learned if it's y is greater than something, you shade the side that is higher than the boundary line, which we'll do sometimes, and not do sometimes. Okay, because we're going to end up calculating the vertices anyways, your graph can be somewhat of a fairly accurate sketch. I don't have graph paper, so your graph can be about as accurate as mine is. Okay, so are there three inequalities here? I'm going to graph all three, and then I'm going to find the solution set. The solution set is the overlapping regions of all three inequalities. So let me go ahead and graph this one. This is y is less than or equal to 3. That's going to be a horizontal line at 3. Even though I'm sketching it, I want it to be kind of realistic. Otherwise, they're going to intersect in the wrong quadrant, and it's going to kind of be a misrepresentation of what's going on. I also have no idea how far to extend this. Let's make it go to 5 because I see there's a 5 in the last equation. Okay, y is less than or equal to 3. Y equals 3 is a horizontal line at y equals 3. It's less than or equal to, so it's going to be a solid line. Okay, I'm not going to actually fully shade it right now, but I'm going to kind of keep in mind which way it's going to go. Since it's the values of y that are less than 3, it's going to be on the lower side of the line. You might want to shade it lightly to give you an idea, but it's going to be below. I wasn't really trying to shade it there, sorry. Okay, now which one am I going to do? I'm going to do this one next. It's already in slope-intercept form. So I'll go ahead and do this one. Okay, the y-intercept is -2. The slope is -2, so down 2 over 1. Is this solid? This is a solid line because it equals. If you have graph paper, your graph will be nicer. I'm trying to make it straight. Okay, and I don't have to consider the shading yet, but I will eventually, so I might want to just kind of think about which side is going to be shaded. This is the y values that are greater than the boundary line, so it's higher than the line, so I'm kind of shading up here. And those highlighted marks are kind of going to be ignored soon. Okay, for the last line, x minus y is less than 5. I could use the intercepts to graph it, and then I just have to be really careful with the shaded region. I'm going to change it to slope-intercept form just so I can do the higher or lower method after that. Okay, so -y. I'm going to move the x to the other side. Then I'm going to divide by -1. Because I divided by a negative on both sides, I do have to switch the inequality. Be careful about that. Okay, so now I'm going to go ahead and graph this thing. The y-intercept is -5. 1, 2, 3, 4, 5. The slope is 1, up 1 over 1. And this is actually a dashed line because it can't equal. Oh, I'm already off, but we're just going to accept that. Okay, because it's in slope-intercept form, and this is a greater than sign, I want to shade the y's that are greater than the boundary line or the y's that are higher than the boundary line. So higher than the boundary line is going to be up here. Okay, now I'm trying to think about where is all the shading kind of overlapping each other. And let's see, so I have to stay below the blue line. So I'm below the blue line, I have to stay above the purple line, which is over here, and I have to stay above the red line. So I can kind of see that that triangle is where I want to be. So I am going to darken the solution region. Oops, don't cross your boundary line, sorry. Okay, so this is the solution region. Every single point within this region is a solution that satisfies all three of the inequalities. It does tell me to label the vertices. So I am going to label the vertices. I'm going to show my work. If you've drawn a very accurate graph, the graph can help you verify that your work is actually correct, which is nice. Okay, and I need to make this line a little longer. Okay, now the vertices are the corners of the solution region. So in this case, it would be this corner right here. And I am going to point out this was a solid line and this was a solid line, which means they both equaled, which is why I have a closed circle here. Okay, between the blue and the red line, this is a solid line and this is a red line. So the red line actually cannot equal to this vertex. So I have to make it open. If either line is dashed, you must use an open circle because that point is not actually included in all three of the inequalities. So for the purple and red intersection, the same is true. One of the lines is dashed, so it's an open circle at the vertex, which means one of these vertices counts as part of the solution region. The other two don't, but I'm still going to identify all three of them. Okay, let me start with the blue and the purple. Okay, since I'm trying to figure out where they cross, I'm thinking of them as equals. So the blue line is y equals 3. The purple line is y equals negative 2x minus 2. If I want to see where they intersect, I'm going to set them, in this case, equal to each other. So 3 equals negative 2x minus 2. I should have put this where I have more room. Oh well. 5 equals negative 2x. So x equals negative 5 halves, which seems realistic given my location. So the x is negative 5 halves. The y is, well, the y is 3 because the line is y equals 3. So that's my first vertex. It does say to show work, so you must show work. But if your graph is accurate, it helps you kind of confirm your answer. Makes you feel better about it. Okay, let me go to the blue and the red line. Okay, so the blue line is y equals 3. The red line, I could use either equation. I'm going to use the original. And I'm putting equals because I'm trying to find their point of intersection. I'm not worried about whether it's included in the solution region. Okay, so let me see. X minus y is 3. So x equals 8. So this vertex should be 8 comma 3 because y equals 3. And that does seem reasonable on my graph. Okay, the third vertex is between the purple and the red line. Okay, the purple equation is y equals negative 2x minus 2. And I'm making it equal again because I'm trying to find their point of intersection. I'm not worried about their solution region. I could use either format for the other one. I think I'll use y equals x minus 5 this time because then I could set them equal to each other. So negative 2x minus 2 equals x minus 5. I got x equals 1. So y equals negative 2 times 1 minus 2. That's negative 4. So this vertex should be 1 comma negative 4. And that does look reasonable given my graph. Okay, so I've graphed the solution set. I labeled the vertices and I showed my work for how I calculated each of the vertices. And the vertices are consistent with the graph I graphed. Okay, we're going to do one more like this. Okay, in this case, let's look at the first one. This is actually going to be a parabola because it's quadratic, which is okay. I just have to make sure I keep that in mind. Okay, I think I'm still going to solve for y. Okay, I'm going to switch the inequality because I am dividing by a negative on both sides. Okay, and then I'm going to go ahead and sketch a graph, a fairly accurate graph. Let's see, I think I'm going to go to 4 because it looks like the second equation is going to go to 4, even though my vertices might end up being a little off. 3, 4, 1, 2, 3, 4. Okay, so the parabola starts at negative, has a vertex at 0, negative 2, and then most of you learned that it goes up 1 on each side, and it goes higher on the right. Is this solid? This is a solid line. Solid parabola, I should say. Well, it's a solid boundary line. Okay, now this is y is greater or equal to this boundary line. So above the line would kind of be this way. The other way would be below. If you're not sure, just look at the vertex. If I shade above the vertex, I end up inside the parabola. Okay, now let me consider the line. I could use intercepts to graph this. That would be fine. Just mark the intercept so I know that's how you did it. But then you just have to be careful about the shading. Y-intercepts 4, down 1 over 1. This is a solid line. Okay, and I'm going to make my parabola a little bit longer on the left so that they do have I can see the vertex better. Okay, now less than this line would be a little lower, so somewhere down here. Okay, so I kind of need to be inside the parabola but below the blue line, which means I'm looking at inside the region. And it does not have to be inside a region. I'll point that out to you after we finish this. Okay, so vertices should be the intersection of two different graphs. So there's a vertex here and a vertex here. I know this is the vertex of the parabola and it's the same wording, but they want the vertex of the solution region. They want the 2 points where each of these graphs intersect. This is the solution region in here. No, I'll point it out now. Okay, if I had shaded way out here in infinity land, that's perfectly acceptable. There would have been only one vertex to that region because it would have had the vertex here and then it would have extended infinitely. If I had shaded all out here, it would have actually ended up with the same two vertices because it would have been the boundary. Okay, so even if it's infinite, there's still vertices to calculate. It might just be different ones. Okay, where should I start with? Let me start with, I want to see where the blue and the orange meet, right? So let's just go with that. Okay, so this is the orange equation. I'm changing it to equals because again, I'm trying to find where they intersect. And I do need to show my work algebraically, even if my graph is amazing. I'm going to use elimination because I can see the y's are already going to cancel. Okay, I got x equals 3 and x equals 2 as my two x coordinates, which looks correct. This looks like x equals -3. This looks like x equals 2. So I think I'm on the right track. Let me plug those back in so I can get the y values. If I plug in -3, I get y is 7. So this is -3, 7 up here. Make sure you label the vertice with the correct point. 2 plus y equals 4. Y is 2, so this vertice must be 2, 2. And that looks okay with my graph since my graph is not on scratch paper. Or it's on scratch paper, not on a graph paper. Okay, for the last example, we're not actually going to graph it today, but in the next section, we are going to do applications and optimization problems. So this is just to kind of give you a preview of that. Okay, so first thing, they're going to kind of describe the situation. So this magic filter can filter air at 12 liters per minute and uses 3 joules of energy per minute to perform the task. The magic filter can filter 8 liters of water per minute and uses 4 joules of energy per minute to do this. Okay, now they're going to add some constraints in this situation so you're going to kind of figure out how to optimize this situation. Okay, the first constraint is that the magic filter can filter more than 343 liters total. It uses no more than 149 joules of energy, and the filter can be used for only 40 minutes. Okay, so for my variables, they normally ask you a question involving the variables so it becomes more obvious, but they didn't this time, so I'm just going to tell you. So X is going to be the number of minutes filtering air. And then I'm going to go ahead and make y the number of minutes filtering the water. There is no particular reason one of these is x versus y. It could have gone either way. Okay, but I define it so that the inequalities are consistent with which quantity is which. Okay, now the first constraint is that the filter can filter more than 343 liters total. It probably should say must filter. Okay, but more than 343 liters total must be greater than 343. Okay, so now I have to think about for the air versus the water, how many liters are filtered for each one. So let me go back up here. Okay, the magic filter can filter air at 12 liters per minute. So for the air, it can filter 12 liters per minute. The air is the x, so that's going to be 12x. Okay, for the water, it can filter 8 liters of water per minute. So 8 liters of water per minute. So that's my first constraint. Okay, the next constraint, it uses no more than 149 joules of energy. So if it's not more than 149, it could be less than 149. It could be equal to 149. Okay, and now I'm looking at the joules used based on the number of minutes filtering air and the number of minutes filtering water. Okay, so where is joules? 12, the air at 3 joules per minute. So the air is 3 per minute. Okay, and then the water is 4 joules per minute, so 4y. This is my second restraint. Let's see what else. The filter can be used for only 40 minutes. Okay, so the number of minutes for the air plus the number of minutes for the water, only 40 minutes means I could use 40 minutes or less, so it must be less than or equal to 40. Okay, those are my 3 restraints that they gave me. You don't have to write these explicitly, but we also keep in mind that x must be greater or equal to 0 because we can't have negative time, and y must be greater or equal to 0. So once we graph these next period, we will keep that in mind even if we don't always explicitly write it.